Welcome back. This is Larry Benko, callsign W0QE, and this video is about plotting impedances in SimSmith and a couple tips regarding how to do this. A few weeks ago, a question was posed on the SimSmith forum asking how to plot impedances on the square chart. Also, a request was made that SimSmith provide a direct method to do this. I meant to try to do a video to address these topics, and I apologize for the delay. I bought a new mountain bike, and then I bought a second new mountain bike, and I've been out biking a lot and running in the mountains, and the weather's been gorgeous, and somehow I sort of forgot about doing this until just a couple days ago. So let me try to address this topic, albeit better late than never, I guess. SimSmith already provides an easy method to plot impedances on a square chart, but we should discuss whether or not this makes sense to even do. The Smith chart was originally developed to graphically solve common RF problems, and the graphical output can aid greatly in understanding the problem. The Smith chart itself can display every real impedance that possibly can exist, and that's no matter where we put the center point in the Smith chart. So there's no reason to plot on any other medium other than the Smith chart itself if it's an issue of just being able to plot the value. All the values are plottable. However, there are good reasons to plot impedance on a format other than the Smith chart. And let's look at, to do this, let's look at an example before we start. This SimSmith window here is a fairly simple window. I got a 50 ohm load that does not vary with frequency. I got an inductor that has a reactance of 50 ohms at 10 megahertz. A capacitor's got a reactance of 50 ohms at 10 megahertz. And both these components have extremely high Qs of 100 million. So they're virtually perfect. And we're going to look at the impedance right here at C1 to ground. And that's what's shown in this plot right here. C1 to ground. And this is what you'd expect. 50 plus J0 at 10 megahertz. I didn't quite get 10 megahertz, but 50 plus J0. And up here, it would be 50 plus J240. And the reason it would be 240 would be this stays 50. This 50 ohms at 10 megahertz becomes 250 ohms at 50 megahertz. Capacitor is minus J50 at 10 megahertz becomes J10 at 50 megahertz. Therefore, it's 250 minus 10, which is plus J240. And likewise, this point down here is 50 minus J240. So does this describe what this circuit does better than plotting it in some other fashion? And that's the purpose of this video. So let's look at the square chart. In the square chart, I've done some stuff already here, but let's get to it a little bit more slowly. There are three, I don't know if these are the three most common, but to me they're the three most obvious ways to want to plot impedance. We can plot it as RS plus J times XS, where RS is a series component resistance, XS is a series component that's a reactance. We can plot it as RP and XP, where RP is a resistance which is in parallel with a reactance, and those two together give you the impedance. We can also plot it as a magnitude and a phase. All three of these ways make very good sense, and they all have value. And based on your understanding of electronics and RF, and based on what kind of a circuit you're working on, one of these may make much better sense than the Smith chart plot of the impedances. And for this example, everything is being the same. We're going from 2 megahertz to 50 megahertz. With this same circuit, we're going to look at the same place. So we plot up here. Notice it says plot right there, PLT. That means in the PLT window here is where we've given this, these, whatever you want to call them, these boxes. We've defined what they are. So we go over here and we click on this. And what we get, make it a little bit bigger. What we get over here is a little more complexity than is necessary, but it's because I did all 6 of these boxes at the same time. I've declared a local variable to be R sub S, and it is the real part of C1.Z. C1.Z is impedance right here, looking this direction. And then I've declared another local variable, $x_s, which is the imaginary part of that impedance. If I want to plot the real part of the impedance, which is 50 ohms, and the imaginary part of the impedance, I plot it in a format like this. And this format is it's in the presenter document on page 9. And the format looks like this. Plot, and there's a style for the line type, and it could be like dots or line or whatever. The name is what actually appears in this box here. And there's a reason to make those names short, and that's because there's only a certain number of boxes that can be put here without the text becoming smaller and smaller and smaller until it becomes unreadable. We have an expression. Expression is what's actually doing the work. Expression would be a formula here. We have an axis name, which is optional, and we have an axis, which is optional. If you leave the axes off, you get Y1. Y1 is the first vertical axis here. If you plot, there's another axis here which is not shown. That would be the power axis. We can make it an SWR. Let me get the power and SWR. So the power axis is right here. The Y1 axis is this. The Y2 axis is this axis, is this right here, and the SWR axis is this. So there's 4 axes that we can use, and we can plot on any one of those, but it makes sense to plot on ones that so you don't get confused. So what we have here right now, and we didn't need to use this local variable to plot. We could have put the real part of C1.z in this form, in this place right here. I chose to make a local variable because I was going to use it here again, and because I was using it twice, I chose to calculate it just once. But if we look at this curve here, we see 50 plus J0, 10 megahertz. Over here we see 50 again plus J240. And 50 minus J240 here. So does this register better with you than this graph, or not? That's your call. Let's get rid of that one for a moment. Let's look at this one. I'm going to move this scale. Let's move this scale down a little bit so we can see a little bit more of it. In this case, we plotted RP, and RP is defined as the series resistance squared plus the series reactance squared, the quantity of those two divided by the resistance, and similarly for X sub P is defined similarly but divided by X sub S. Those formulas are in every handbook that there is. I think they're in the antenna book too. They're very common, and we've chosen to plot the real part on axis Y1, the imaginary part on axis Y2, just like we did before for the RS plus JXS. And what we see here is at 10 megahertz, we see right here, basically it's the red dotted line here is the parallel resistance, and it's 50 ohms. And that is in parallel with a reactance, which is in the process of transitioning from minus infinity to plus infinity here. So effectively, this reactance is infinity. This line is just unfortunate. It goes through here. But if we plotted dots instead of that, there wouldn't be a dot. The dot would be at the endpoints. So it's 50 in parallel with an infinite impedance, which is, again, just 50 ohms. And what we can see happens here is the real part appears to get larger as we go up in frequency because it gets out of the way and it's dominated by the reactive piece. The reactive piece comes down and then it rises again. And that's again due to the combination of the resistance that's in parallel with it. Does this resonate better with you? And again, I can't make that decision. Only you can make the decision as to whether that's a better way to plot it or not a better way to plot it. And finally, we can plot like this. And this one resonates with me a little bit better than the other two did generally. But what we are plotting here is we're plotting. SimSmith has already built into it a function called magnitude. We can look at the magnitude of the impedance, and we can look at the phase angle of the impedance. And when we do that, unfortunately, this says ohms. It says ohms because I defined the axes over here to be ohms, but I want it in degrees. So I really could, if I was plotting this and this at the same time, I could either get rid of this, or I could say I mean, heck, you can do anything you want to do. I could do ohms, dash, degrees here. If that meant more to you, I could just not plot these two and just change the axis here. You can do as you wish in that case. But looking at the graph itself, what I see here is at 10 megahertz, I see a magnitude of 50 ohms for the impedance, phase angle is 0. And as I go up in frequency to 50 megahertz, I see a phase angle of about 78 degrees. It's positive, which means it's inductive, which it is. And down here at 2 megahertz, it's again 78.2 degrees. And it's negative, which means it's capacitive. Does this resonate better with you? You know, I can't really define which one of these is the best one. We have four choices here. We could define impedance other ways. You can define impedance as an imaginary part of impedance and a Q, and that will give you the values. Different industries do it different ways. Different people think differently. Nevertheless, it gives you a lot of choices to do, and SimSmith does all these just fine. So back to the point of the suggestion about having a box for SimSmith to use. Which one of these would you want to plot, or which set of these would you want to plot? If you made one of them be the primary one, the others would be left out. And in my opinion, they're all probably just about equal in terms of need. So rather than singling one out, I kind of preferred to leave SimSmith the way it is. Ward, of course, you know, he codes it, so he does as he wishes. But nevertheless, that's my reason for thinking that we don't want to do that. Plus, this real estate down here is incredibly valuable. It's incredibly valuable. And that's why I find myself always making these labels small in terms of length so that I can fit more of them in on the line. Once the line gets filled to a certain point, like up to here, then these boxes get smaller, the text gets smaller, and small text becomes unreadable at some point in time. And you can do an awful lot of calculations in here. Likewise, this is all based on plotting impedance at this one point right here. We could plot impedance at this point looking to the left. We could plot impedance here looking to the left. We could plot impedance from here to here. These let me get rid of these, get rid of the comments in these next three lines. And why doesn't this work? Oh, this doesn't work because here's a case where we've defined the y2 axis to have another label different than it was defined up above. Now it works. I didn't need to delete this line. I just need to delete the other one. And when I'm done down here, usually I need to say, oh no, I did need to delete both of those because I'm defining both this axis and this axis, giving them a name. So by deleting them up here where I'd given them the name earlier, we're good to go. And now it says R and X up here. Let's get rid of all this. And now what I have is I have a real part to this impedance, an imaginary part. And what I'm calculating here is the impedance from here, which is C1Z to ground, minus the impedance from L to ground. And that's the impedance across these two components. And by doing that, you get exactly what you'd expect to have a series resonance circuit. At the resonance point, it has 0 ohms reactance. Above it, it's inductive. Below it, it's capacitive. Also, I can plot that same impedance on the Smith chart. We don't see anything here, but if we go back to Smith chart, we see a new box here, which is entitled Z. If I turn Z on like that, I get this blue curve. This blue curve, this is 0 minus J240. I'm not quite on the box. This is 0 plus J240. This is 0 plus J0, which is exactly what these two components in series are. So there's many different impedances we might want to calculate. If we were to put something in the circuit like a ruse block, we can have all kinds of components in here. We might want to look at impedances of many of those. And it becomes impractical to have a box here that just basically gives you a one-click plotting of those. So that's kind of my take on the idea of having a box to directly plot. Now, as far as how we graph these things, I mentioned three cases here that were different than the Smith chart. We might also want to do a few other things. The reason to plot in a specific format should be based on what makes the most sense to you. Usually, There are many times, though, where you're collaborating with somebody, and that person you're collaborating with doesn't understand it. So doesn't understand what you're trying to convey. So you need to change how you're plotting things to probably make it a little bit more, a little more useful to that person. If you are writing an article for a magazine or some trade journal or whatever, they may say they don't want it in a certain format, the data. You may be doing a project at work, in which case they've edicted how the format's supposed to be. In those cases, it overrides what you believe to be the most useful format, and you need to follow what someone else has done. The next example that I'm going to do here deals with the ARRL Antenna Handbook. Every version of the ARRL Antenna Handbook has an example in Chapter 2, which is titled Antenna Fundamentals, of a 100-foot long dipole of varying wire diameters, and it plots impedance versus frequency. And it plots that impedance in a manner where the x-axis on a square chart is the log of the resistance, the y-axis is the reactance. Why they chose that format, I don't know, but they've done that for years. And it's a plot we see in the handbook, and it's been there for as long as I can remember. Let's see if we can get SimSmith to help us do that, allow us to make that kind of a plot. I don't believe SimSmith can directly do it, but let's just get SimSmith to write the data out and put it in another program and see what we can get. So what I did, I started off here and I created a file from the EasyNet, the last z.txt file that EasyNet writes whenever you do an SWR plot, and I say load that, and there it is. And here's what I get. Here's a plot of a 100-foot dipole, the impedance of it, looking at 200 kilohertz steps. So here's 4.6 megahertz, 4.8. We see it's resonant for the fundamentals about 4.8 megahertz, which should be right for a 100-foot dipole, 5, etc. And SimSmith draws a straight line between those points because I specified for it to do it in 200 kilohertz steps. Had I specified it to do it in a different number of steps, SimSmith would have still drawn through the points, but it would have smoothed the curve out for us. And that may be more palatable to looking at it. But in reality, that's the data is only at the points where there's a vertex. So here's my data, and my data looks like, let me go get the file here. There's the file that was put into SimSmith. SimSmith is smart enough to look at an EasyNet file and read the frequency column out, which is the first column. It reads out the R and X, which are the third and fourth columns, and it ignores the rest of this. And it plots that, and everything's good. Now let's pretend we did something in here that changed the impedance somehow. It doesn't really matter how we're going to change it. I'm not going to do anything, but we're going to change it. And then we're going to write the data back out. So we write the data out with a format like this, and we're going to write our new file, which will have frequency as the top line, R and JX, and then lines of data that have these three fields in them for as long as we need to, and we'll plot the impedance here to ground. So we do that by going over here, File, Write Plot Result Files. We go pick a file, which is here. I've already written this file, but we're just going to write it again. And we say Save. And I'll go over here and get the file. And there's the file that SimSmith created. Now this file was simpler than the EasyNet file we brought in because this only contains the data we needed. We can see it's comma separated, so we can put it into Excel if we want to. We can see that it runs from 1 megahertz to 30 megahertz, which is exactly what is done in the ARRL handbook. And let's see if we'll see what we can do. So I've already done this in Excel, and this is Excel 2016. But I read the file in, and here's my data values again. And we can see it goes from 1 to 30 megahertz. We have an R and an X field. And the first thing I did was a simple scatter plot, and I let Excel figure it out. Excel gave me frequency on the x-axis as we expect, and it gave me one axis here, which is both R and JX. And we can see the resistive piece, which is blue, rises to the half wave point, and then back again to the 1.5 wavelengths points and the 5 half wavelengths points. We can see it go through, the reactants go through 0 here at the resonant point, and here's a resonant, 3 times the resonant point. But we see down here it's basically 4.8 megahertz, which is about what it was before. This is the standard curve that we might be used to. However, that's not what's in the handbook. What's in the handbook is a curve that looks like this. And this curve can be made to be done in Excel. It's probably out of the realm of doing it on this video. But what we do in Excel is we choose to use this axis as the plot axis for the x-axis. We choose to use this set of values for the y-axis. So we have log of resistance going this way. This is resistance, and we see that it's log because I specified that this be a log axis. I specified this to be a linear axis. Couldn't be log because it's got negative values in it. And then I chose to put category labels on the dots. Now I put them every 5th one, which was a little tricky to make happen, but you can do it. And this matches what's in the ARRL handbook very, very closely. So here's another example of plotting impedance. Here we don't have 2 dots anymore to plot a single impedance point. We have a single one, and this may mean more to you. To me, it doesn't make more sense to me than the original plot we had on SimSmith, because somebody might get to be drawn to the conclusion that this is a good place for the antenna to operate at because we've got a lot of frequencies that are near this impedance point. We do, but it's 100 ohms. It's not a 50 ohm impedance point. It's 100 ohms. So that's 2-to-1 SWR. You can't read SWR off this curve. I don't know if this is a good plot or bad plot. It's something, again, that's one of those things where somebody's done it and you say to yourself, could I make that same plot? And the answer is you can. SimSmith can help us do it. I don't know that SimSmith can do this directly or not. It probably really doesn't matter. You know, different industries talk about impedances differently. I had a case a while back where I had some toroids that weren't working properly, and I plotted out the impedance of the toroids versus frequency, and you could see that they were resistive where they should have been. They had too much of a resistive component where they should have had a reactive component. And I sent the people a Smith chart that showed that impedance, and they looked at me and said they had no clue what it was. So I had to convert it to an R plus JX plot, and they still didn't like that. It wasn't until I converted to a magnitude in phase did they get it. And they could see that the phase was only about 85 degrees instead of like 89 degrees. And that was why the toroids were heating up. So this is an example of who you deal with and who you're talking to may want the formats to be different. Hope you found this interesting, and perhaps this will spur some more comments. But again, like I said, I don't know that SimSmith should be responsible for doing all this work. These are probably some pretty fringe uses of SimSmith. Hope you've enjoyed this, and thanks for watching.